Continue on here, wrap up this chapter, not too far from the end. Last time we put that around. Last time we were talking about really the relationship between temperature and the rates of reaction. We saw really two versions of the Arrhenius equation. One version really is a more graphical sort of version where you take the natural log of K on the Y, you graph 1 over the temperature in Kelvin. And if you do that, that should yield you a linear line with a negative sloping line. And the slope in this case would equal negative E of A over R. That would, again, graphically allow you to determine the activation energy, which obviously is what E of A is, by using the slope. A reminder again, that line is a negative sloping line. So negative and negative here are important. Because again, when you solve for your activation energy, it should be a positive number when it's all said and done. We also can find what's referred to as the frequency factor, and that is the y-intercept is the natural log of the frequency factor. So basically where it crosses, the frequency factor, as we talked about, is basically the proportion of molecules that have enough energy to kind of get up and over the hill to the other side. And you could graphically sort of calculate that. So there's sort of a graphical version of this equation. There's also a 2-point version of this equation where, technically speaking, if you know 2 points along this line, you can just kind of plug and chug into the equation and solve for what you're looking for. And that is the natural log of K2 over K1 equals E of A over R, 1 over T1 and 1 over T2. Once again, here our temperatures do need to be in Kelvin. Our R's, our gas constant, remember that it is the one with energy. So 8.314 joules per Kelvin per mole. These are obviously two rate constants at two different temperatures. And again, you could actually use this equation to solve for pretty much everything. You can use it to solve for activation energy. You can use it to solve for a temperature. You can use it to solve for a rate constant. Obviously, if you know the other pieces of information along the way. When you're using this equation, again, two very common mistake that people make that we talked about is right here, unit-wise. Again, E of A is typically kilojoules. And obviously here are our values in joules. So you got that 1,000-fold conversion. You got to make sure you could go either way. You could either convert everybody to kilojoules or everybody to joules. It doesn't really matter. The other one, again, is very commonly people will forget to convert these guys into Kelvin. So that's also a very common mistake. They'll use the Celsius. And that oftentimes is because sometimes questions will ask for the answer in Celsius and they give the temperature in Celsius. So people just think they could just kind of leave it in Celsius when they do the calculation. So you do need to make sure you convert it to Kelvin and then if necessary, kind of convert it out afterwards. We ended last time sort of talking about reaction mechanisms. And reaction mechanisms are basically sort of an explanation of how a particular reaction may take place. It is a sort of pathway to get to your reaction that may include multiple individual sort of reactions. So those kind of individual reactions are sometimes referred to as elementary steps or reactions. And when we look at a mechanism, there's a couple of different types of mechanism problems that we come across, but one type is, is this sort of a good or bad mechanism? Is a very common sort of problem. And the way you can determine whether or not it's sort of good or bad is there's two things you really have to look at. One is very simply, if you add up all the steps, does it actually equal the reaction you're looking for? So clearly, if you have a possible mechanism and you add together all those steps and it doesn't equal the reaction you're looking at, then it's probably not the greatest mechanism there. So it's probably not a good mechanism. Remember that when we're adding equations, right, anything on opposite sides can cancel or reduce down regardless of which sides they are. Whatever's left over on the left stays on the left. Whatever's left over on the right stays on the right. And just kind of bring it down when you add them together. Secondly is the rate determining step, the RDS. That is the slow step in the mechanism. And that should have a rate law that equals the experimentally found rate law. So usually a lot of times in these type of problems, they will give you sort of the experimentally found rate law, and the rate determining step should have a rate law that matches. So one of the major differences when we're doing reaction mechanisms and kind of normal regular kinetics is we actually can, when we're looking at these elementary steps in a mechanism, we could actually use the coefficients as the orders. So for every elementary step within a mechanism, we could actually write a rate law, again, just using the coefficients. We really can't do that anywhere else in kinetics. It just applies to kind of to this specific part where we're doing some type of mechanism type problem. So one way you could determine what is the rate determining step is if you write the rate law for each of the elementary steps and one of them matches, like I think the example we did at the very end there, it matches the one that was found experimentally, then you know that is your slow step in the mechanism. The rate determining step is the slow step that basically determines the overall rate of the reaction, because it's going to take the longest process is that step, basically. And once that step's sort of over, then the reaction will kind of proceed at a pretty good pace. But that's sort of your limiting sort of step there in terms of the rate. Another way that you can recognize whether or not something is sort of the rate determining step or not is sometimes in problems they will list each step as like fast, or they'll list a step as slow. And the one that's listed as slow would be your rate determining step. So that is sort of how you do that. Any questions on any of that stuff there we talked about last time? Okay. Then let's take a look at a couple different types of mechanism problems here. So I think we didn't actually do this one, but we kind of stopped, I believe, if I'm not mistaken. So we're looking for this overall reaction, which is 2H2 plus 2NO. And we're going to 2H2O and a little N2 action there. And the observed rate law, or really the experimental rate law, is K is equal to, no, that equals K. There we go. I'll try that again. Too many equals, not good. I'll try that. All right, so it is K times the H2 concentration times the NO squared in this case. So what we want to do in this type of mechanism problem is they give you obviously the rate law that was found experimentally. They give you, again, the reaction that you're looking for. And this is sort of a plausible mechanism for how this reaction may take place. So this is one type of problem, like I mentioned at the very end last time, where you got to kind of prove that either this is sort of a good or bad mechanism. So again, what you want to really do first off is just to kind of go through the two things that you need to know to determine if it's a good or bad mechanism. And one of the things is you need to add everybody together and make sure that you do get the overall reaction that we're looking for. So in this case, if we look, we got a little N2O canceling out. We got a little bit of anything else there. N2O2 also canceling out. And I think that is everything. So everybody on the left-hand side of those arrows stays there. So we got 2NO plus 1, 2 H2 on the left goes to 1, 2 H2O on the right, and then N2. So this is the first sort of process here to determine if this mechanism is good. When you add up all those steps, it does actually hit the reaction that we're looking for. So once again, if you did this step here and you add it together and it does not equal that reaction you're looking for, then clearly it's not a good mechanism, right? So that's a way you could kind of toss it out. Now that it is sort of a good mechanism in the sense that it does add up to the reaction we're looking for, the next thing we want to determine is it really a good mechanism overall? So to do that, we know that the rate determining step should have a rate law that equals the observed rate law or the experimental rate law, right? So in this case, we want to go back through our possible mechanisms here, and I'm just going to erase these X's here. And we want to identify the rate determining step, which is basically the slow step. So in this case, which one would be the rate determining step? Yeah, so is step number 2, and frankly, that's all you need to see right there, which is it's slow. So that's going to tell you that this step here is your rate determining step. So this step should have a rate law that matches the one that was found experimentally if it is a good mechanism. Now, because this is a mechanism problem, these are elementary steps, we could actually write a rate law straight from the actual step. And if we do that, we could write that the rate is equal to K times H2 times N2O2. Now, what we want to then do is compare the rate law for the slow step to the one that was found experimentally. So rate law here and our experimentally rate law, do they match? The answer is you really don't know. Even though you may look at it and think it does not match, we really don't know. And the reason we really don't know is we have to kind of be able to compare apples to apples, as the old saying says. So right now we have a little issue with the rate law that we have for the slow step, because when I look at this guy right here in this reaction, that is something that is a intermediate, right? So if we go back to a crossing out, that is something that gets crossed out, and it is not found in the overall reaction, is an intermediate. So because our rate law for our slow step has that intermediate in it, we cannot directly compare the experimentally found one, because again, you got to kind of compare apples to apples and things that are the same. So we have to actually do a little bit of math to manipulate this rate law and get rid of the intermediate and leave us hopefully with something that is everything in the overall reaction. So to do that, our goal here is we want to kind of get rid of, and again, I'm just going to erase these guys again. We want to get rid of our intermediate and substitute this intermediate for something else. So when we look at the intermediate that's here, really the only other step where we see that guy is step number 1. It's basically the only other step where we actually see that. Now, step number 1 is actually a reversible reaction. There is arrows actually heading in both directions. So there is a forward direction in this reaction that has a K value associated with it. And there's a reverse direction in this reaction that has a K value associated with it. So the reaction as it goes from reactants to products is known as the forward direction. And as the products recombine and make reactants, that is known as the reverse direction. So we could actually, because this is a reversible reaction, we could actually write 2 separate rate laws for this, one for the forward direction and one for the reverse direction. So if we were to write the rate law here for, I'll call it the forward direction for the F, that means it's like a normal reaction, reactants to products. So we would do the K times NO, and we would square it again because of the coefficient that is there. We could also write the rate law for the reverse reaction. I'll put an R there for reverse reaction. Now, when we're talking about this reverse reaction, it is our products going to our reactants, which means in this case, technically our products are our reactants in this case, right? Is their starting stuff. So we would actually write a rate law where the rate is equal to K times N2O2. Again, because we're heading in this direction, so we're starting with these guys. So that's what goes in the rate law. As opposed to the forward direction, we're starting over here and heading that way to the right. First off, any questions on that? As we'll talk about in the next chapter for sure, this reaction, because it's reversal, will eventually reach what's known as equilibrium, which means essentially the rate of the forward direction here will equal the rate of the reverse direction. So the rate of the forward direction will equal the rate of the reverse direction. And that's really good because although we do not know what this number is, we do know that they are the same number, which means you can actually then set these two guys equal to each other. And that would get me that K NO squared equals K N2O2. And if we want to be really specific here based on the actual mechanism, really this is K1 in that mechanism, and this is K to the -1 in the reverse direction. And I could put that in here as well. Doesn't really matter. First off, any questions on that? The goal again is to do what? The goal here is to get rid of our intermediate, right? So I now have my intermediate over here, and I can isolate it by dividing that K value to the other side. And that would give me K1 times NO squared divided by K to the minus 1 equals N2O2 in this case. At this point, I now have, if I could get that, there you go. I now have this, which basically equals this. And now I have really what I need to substitute into here. So I could take this entire thing and substitute it into my original rate law that I wrote for that second step. And if I do that, I will end up with the rate equals K H2, and I'm just going to write everything out, K1 NO squared divided by K to the minus 1, right? Now, at this point, I have 1, 2, 3 K values, right? And K values are the rate what? The rate constant, which means are those numbers the same or different? They are the same. So 2 of these guys, although we don't know what it is, are going to cancel out basically. And that will then give me the rate is equal to K times H2 NO squared in this case, right? Now I have a rate law where I have got rid of the intermediate, and now I can actually compare it to the one that was found experimentally. And do they match now? They actually do match, right? So the one we found based on the mechanism, once we got rid of the intermediate, actually will match that one. So they do match, which is good. So this is a good mechanism, right? Most likely referred to as a good plausible mechanism, right? It plausibly could occur this method. So in these type of mechanism problems, you're given the overall reaction, you're given the experimentally found rate law. You have to use the mechanism and the rate determining step and probably do a little math and substitution out there to get to a rate law where you can compare the two, the experimental one and the one found from the mechanism, and see if they match. Clearly, in this case, it did match, which means this is a good or plausible mechanism. Again, if you got to this point and the mechanism we just found or the rate law we found did not match the one that was experimentally, it would be a bad mechanism, right? So those two things do have to match. Any questions about there? All right, I tried one, you try one. I think that's how that works. All right. So here we want to show if the proposed mechanism for this reaction matches the observed rate law. The 2's up here, so I'll just move the 2 down here. There we go. All right, so that's our overall reaction. That's the experimentally found rate law. That's the proposed mechanism. Show that it matches or does not match. Is this sort of a good or bad mechanism? So take a few moments, see what you come up with. Remember, in order for this type of mechanism problem, again, we're given the overall reaction and we're given the experimentally found rate law. So again, to determine if it is a good or bad mechanism, we need to make sure basically 2 things match. We need to make sure when we add the overall reaction together, we do get the reaction that we're looking at here, which is this guy. So let's just start with that. We're going to take this, we're going to add it together. We're going to look for any intermediates or stuff that can cancel out. Again, looks like the O will do that. And I think that's it. So everybody on the left there is going to give us 203. On the right, we got 102 and 202s. That's 302s. So that's a check there for the first thing that needs to happen for this mechanism to be a good mechanism is when we add up each of those steps, obviously it equals the overall reaction. Any questions on that there? Next, we need to turn our attention to basically the rate determining step, which in this case we could identify as which step? Is number 2, and we know that because frankly it just says slow basically. So that is our RDS, or rate determining step. That means that the rate law for that step, again, if it's a good mechanism, should match the one that they found experimentally. We can write a rate law directly from this step because it's an elementary step. So the rate is equal to K times O3, and O, the 2 here is just the step number, right? So again, we want to compare this rate law to this rate law. we are also going to run into a problem because in our rate law here, we have a intermediate, right? So just like in the last one, we need to kind of get rid of that so that we could clearly compare the two rate laws. So in this case, it makes it pretty simple. We actually only have one step to deal with. There's only one step possible. So the place where we want to look again is here. And once again, we do have a reversible reaction where we have, again, the forward direction and we have the reverse direction basically occurring. So that, like we saw previously, will allow us to write two separate rate laws, one for the forward direction and one for the reverse direction. So if we write the rate law there for the first step for the forward direction, reactants to products, that would be K is equal, or K times the O3. If we write it for the reverse direction, that would be the products are basically our reactants. We would have the rates equal to K times O2 times O. First off, any questions on that? And again, both of these rate laws come from obviously the first step there. At this point, much like we talked about a second ago, the rate of each of those, although we don't know them, because it's a reversible reaction, will reach equilibrium and they actually will equal each other. So once again, that is going to allow us to set these two guys equal to each other, right? And that will get us K, and again, I'll put the little numbers there, 1 and -1. K1 times O3 is equal to K to the -1, O2, and O, as I try to squeeze it in there at the end. Once again, remember that ultimately we want to get rid of O in this case. So we're going to take all these guys and divide it to the other side. And that would get us that basically O is going to equal K1 O3 divided by K to the -1 O2. That is what we're going to use now to substitute into our original rate law at this point. Now, when I do that, I'm going to put everybody in there all at once here. And again, I won't cancel anything at this point. Actually, I'll get rid of this here. So I got a little space to write it here, I think. All right. So that would get us that the rate is equal to K times O3. And now I'm going to substitute in what I got there on the bottom, which is K to the -1 O3 divided by K to the -1 O2 there. Just like previously, this is going to cancel. Two of those K values are going to cancel because they're the same number. Now I could also clean it up a little bit here. That would get me the rate is equal to K. I have an O2, an O3 times an O3 up on top. That's going to give me O3 squared divided by O2. Yeah. Now we have a rate law again that we got rid of the intermediate, and we could compare this rate law to this rate law. Do they match? They do match. Again, to the -1 means 1 over O2, which puts it on the bottom, right? So that is what that means. This is essentially O3 squared and basically 1 over O2. That is basically what that means, right? So to the -1 would be 1 over our O2. That's basically what that means. So they actually do match here. So we have both things that we need to know. This is a good mechanism. Overall reaction matches. Rate law from the mechanism matches the one found experimentally. And again, this would be a plausible mechanism in this case. Any questions on that there? So this is also a very common sort of mechanism problem where, again, you sort of have the mechanism, you have the reaction, you have the rate law experimentally found, and you just need to kind of use it to prove that it's good or bad. And again, in this case, if those rate laws did not match, then it would be a bad mechanism there. You know? Any questions on that? All right. So let's try one more here. Determine the overall reaction for this mechanism. Also determine which one is the rate determining step. identify any intermediates in this case. Let's see what you so a little different type of mechanism problem. In this case, we want to kind of come up with everything based off of the mechanism that we see. So in this case, we could obviously come up with the overall reaction like we've been doing by simply just adding them together. In this case, it does look like B there will cancel. And I think that's actually everything that will cancel. And that will give us basically 2A on the left plus B to the 2 and 2AB there as our overall reaction in this case. Now, we want to determine the rate law, and what we know is in a mechanism, right, the rate determining step should have a rate law that matches the one found experimentally. And once again, we can ID the rate determining step here as the first step, as that's the slowest step in this mechanism. And that means that really the rate law that we get for that first step should be the rate law for this reaction. So if we write the rate law for that first step, it is K times A times B to the 2. And again, that rate law is good. It actually does not have any intermediates in it, right? So we're all good on that. Speaking of intermediates, the intermediate in this case is only B, right? That's the only thing that got canceled out. Remember that an intermediate is something that is formed early on in the mechanism, but gets completely used up by the time the reaction's over, and it is not found in the overall reaction, right? So that is what an intermediate. I think maybe on the first one we had one where we reduced down something, but it was still in the overall reaction. So again, that's not considered an intermediate. It cannot be in the overall reaction. Any questions on this one? Yeah. Say it one more time. Go side before this one. Yeah. Yeah. Other questions? Okay. Then a catalyst, as we talked about earlier on, is again a substance that is not a reactant. It's not a product. It does not get used up in the reaction. Again, as we talked about, it really is there to facilitate that reaction occurring a lot more efficiently and finding an alternative way for that reaction to take place. Much more energy efficient way, if you want to think about it that way, for that reaction to take place. Ultimately, by allowing that reaction to sort of more efficiently occur, what it ultimately does, as we can see here between our energy diagrams of a uncatalyzed reaction versus a catalyzed reaction, is instead of in the uncatalyzed reaction, those reactants got to climb this bigger hill to get to the other side. What happens is actually it lowers the activation energy. And the result of that is we now have a much smaller hill that everybody has to climb to get to the other side. And what that's going to do is allow, again, more reactants to have enough energy basically to get up and over to the other side. The result of that is you typically will see the reaction rate increase as a result of that. Most of the time when we talk about a catalyst, we do talk about it in the sense of it increasing the rate of reaction. There are what are referred to sometimes as negative catalysts, which basically will slow down a particular reaction. But I would say 99% of the time people talk about it in terms of speeding up the reaction. Ultimately, it does that again by lowering that activation energy. You oftentimes in an equation will see the catalyst written up there on top of the arrow. That's usually where you'll see a catalyst. And again, it could be something like a metal like platinum. It could be something like H+, which indicates it's an acid being used as a catalyst or something like that. So usually they'll put those things on top of the arrow there. So the catalyst lowers that activation energy. The result of that is, again, an increase in the rate constant and the rate of the reaction. Now, there are different types of catalysts. There are some catalysts that are, for example, in the same phase as everybody else is reacting. And there are catalysts that are in different phases of what is reacting. And that is the difference between, say, a heterogeneous catalyst and a homogeneous catalyst. Just like mixtures, heterogeneous means you see different layers and phases. And that's the same thing here. Our catalyst and what's reacting are in different phases, like the Haber synthesis of ammonia. Ammonia is a spontaneous reaction, but it does take all day. So you need some type of catalyst to kind of allow that to occur. The production of nitric acid also as well. In your cars, if you have a catalytic converter, you have they have different catalysts in those catalytic converters that will help in the process of breaking down some pollutants before they go out your tailpipe. Homogeneous catalysts are usually in the same phase, and sometimes you may use an acid as a catalyst or a base as a catalyst. And if that's the case, it's probably some type of reaction where everybody's in the aqueous phase and everybody's floating around in the solution basically together. The pH that they would provide, the acid or the base, provides the right environment for that reaction to occur much more efficiently than if the pH was maybe a different, either higher or lower, depending on the situation. So here's that Haber process with ammonia. You can see some solid catalysts kind of being used. And as I mentioned before, in this sort of idea, what happens is this is our catalyst. And essentially, without the catalyst there, these gas molecules, again, kind of fly around and find each other to react. The catalyst kind of helps everybody down to the same location. That's also going to assist in collisions that's going to occur once they get there. It also helps actually break some bonds and start making some bonds over here, and releases obviously our products a lot faster and again more efficient than if the catalyst wasn't there and they just got to fly around and try to find each other and stuff like that. So you can kind of think of it like it brings everybody to a central location, and that's going to obviously increase the chances of collisions occurring and the reaction starting to take place a lot faster. There's nitric acid, which uses platinum as a catalyst, and we use some ammonia, some oxygen, makes some NO here. The NO makes some NO2, eventually makes some nitric acid, and also makes some nitrous acid as well, which actually can make a little bit more of our NO2, which then can make some more nitric acid along the way. Here's catalytic converters in your car. Again, it helps with sort of the not allowing out your tailpipe of your car or a lot of pollutants. There's actually two chambers usually in a catalytic converter, and one takes care of some unburned hydrocarbons, other ones take care of some nitrogen and stuff like that. And again, it converts it into things that are less pollutant along the way. It helps in that reaction, which obviously oxygen that goes through there as well when you do that. That's also why people steal catalytic converters, yes, because they have a lot of good metals in there, right, that are used as a catalyst and stuff like that. So, hopefully don't go to the parking lot, your catalytic converter is gone. All right, so a reminder, right, we are quizzing up on Tuesday on Chapter 12, so everything in Chapter 12, bless you, is fair game. We'll take that at the beginning of lecture on Tuesday. So now we're going to get into really the class for real, unlike the kinetics part, but we're going to get into really the main topic of the class, which is equilibrium. So we're going to talk about chemical equilibrium in this reaction. And as I mentioned before, it is really the main sort of topic of this class. We'll talk about every equilibrium. Again, you probably never want to learn about, but you will. And when we talk about equilibrium, it actually involves reactions that we sort of just saw there when we were looking at mechanisms. It involves a certain type of reaction, and these are reversible reactions. So when we talk about equilibrium reactions, we will have these reversible reactions, which, as we saw in those sort of mechanisms, have arrows that head in both directions. Now, you may have seen these type of reactions in 50 when you talked about weak electrolytes and stuff like that. These are these ones that kind of go back and forth. They do have two directions, as I talked about a second ago. As you go from reactants to products, that is what is known as the forward direction. And at some point when this reaction occurs, you will build up enough products that those products will decide we would like to go back the other way. And those products will recombine and actually head in the opposite direction towards the reactants. And again, that is what is known as the reverse direction. And this will continue until what is referred to as chemical equilibrium is reached. Now, when people hear chemical equilibrium, they have equal in their head. And because it sounds like equal, when you say equilibrium. And people oftentimes assume that when something reaches chemical equilibrium, what you have on the reactant side and what you have on the product side are equal to each other. You got equal amounts on both sides. And that is not what chemical equilibrium actually means. What it means is actually what we were talking about in the last chapter. It is those rates of the forward reaction and the rate of the reverse reaction will actually equal each other. So when something reaches equilibrium, it really means, as we'll see a number of times here, the rate of that forward direction will equal the rate of the reverse direction. So what does that mean? It does not necessarily mean that you end up with the exact same numbers on both sides of everybody. It means that when it reaches equilibrium, it will lock into place the concentration of everybody at that point. Whatever that concentration may be, they basically get locked into place. Also, it may lock in their pressures if you're dealing with pressures rather than concentrations. It will lock everybody's pressures into place because just as quick as it kind of goes to the product side and loses something, it will just come right back at the same rate, right? So it's a net no change that's going to occur. Everybody gets locked into place in terms of where they're at. So what that means is, again, if we started with something, if we started initially with like 2 molar of this guy and 4 molar of this guy and nothing, and we end up at equilibrium when it reaches, maybe we got 1 molar of this guy, 3 molars of this guy, 2 molar of that guy, and like 4 molar of that guy. What that means is once it reaches equilibrium, those concentrations for everybody will always be that number. Unless you do something to screw up the equilibrium, which you can, and we'll talk about later on. But if you don't do anything to it, it will just be able to maintain basically their concentrations because those rates basically equal each other. So as soon as something gets lost, it comes right on back and nothing really ultimately changes. So one of the first misconceptions, again, is people sometimes think when it's all done, I should have like, 2 molar, 2 molar, 2 molar, 2 molar, everybody should be equal. And that's not the case. So that's what we're talking about. We're actually talking about the kinetics of it, actually. Those rates of the forward and reverse direction will equal each other. Now, when you look at a reaction that is reached equilibrium, for example, let's just say you did something, a reaction, and it reaches equilibrium, and it looks red to you, right? Maybe it was yellow and colorless, and you poured some stuff together, and it becomes red. And to you, it looks red, and it stays looking red. It's sitting there in the beaker, and it looks red. And to you, it looks like perhaps that the reaction is done, right? It's over, nothing's happening. Thing turned red. It's not turning any other color. It's just keeping it red. So although it may look to you sort of on the macroscopic level, the big level, that nothing's going on, if you were able to just zoom into that beaker, and let's just say that this was the reaction we were looking at, you would see a lot of A plus B going to C plus D, and a lot of those guys going back and forth. So there's a lot of activity continuing to happen, even though when you look at it on the big scale, the beaker just looks red and it's done, basically. So there's a lot of activity that has to happen to keep it, for example, at that color. So sometimes people think it's like done at some point. There is just constant activity happening in these type of reactions, back and forth, back and forth. It is different than sort of a one-way street reaction where you have just one arrow going to the products. In that case, everybody's going to dump out on the product sides. Not too much is coming back at all the other way, right? So it's all just going to kind of go in a one direction type of situation. So as I mentioned, when we talk about chemical equilibrium, it's a state where the concentration of the reactants and products basically hit a point where they just constantly remain the same throughout time. Again, we also can deal with pressures, as I mentioned before. So you can have an equilibrium that involves pressures, and the pressures would again remain constant throughout. The reason the pressures remain constant throughout is because the concentrations of those guys remain the same. So if you have the same amount of gas molecules flying around, you're going to have the same pressure basically happening. There's no increase or decrease in the gas molecules that are happening at that particular point. So as I mentioned before, on the molecular level, there's a lot of activity to maintain that equilibrium. But again, it may not look like there's a lot going on if you just kind of look at like the beaker and stuff like that. So on the macroscopic level, it looks static, but microscopically, it is dynamic and a lot of stuff is happening. So if we look at this reaction, which is basically the formation of ammonia, a little H2 plus some N2, going with a little NH3, I'll balance it like I'm in chemistry class here. There we go. And initially, in this case, when we look at this, we have just reactants. So initially here, it is just reactants that is present. We have basically here no products, basically, at the beginning. And because of that, when we think about this reaction, if I have only reactants and I have no products to start with, which way is this reaction has to head? Yeah, the only option for it is the forward direction, right? You have no products, you can't go backwards. So you have at the very beginning of this reaction, definitely that forward direction occurring. At some point, you will start to build up some products. And we see that forward direction here when we look at our reactants, they start to decrease as time is going on. In the same moment there, we're starting to actually now see some products being made, right? So we're starting to make some products as we're using our reactants. At some point, what you will see is as we continue to make products and we continue to use reactants, you will eventually make enough products that will allow the reverse reaction basically to start to kick in. And we see that because as we start to do that, the amount of reactants here are not decreasing as steeply, right? They're starting to level off a little bit. And we also start to see that the product formation is also not increasing as steeply, right? It's starting to level off at some point as well. And eventually, as that reverse reaction starts to kick in along with the forward reaction, they will equal the same rate. And we can see that in this graph where right about here for all of them, they all plateau out, they all level off. So if they're all running pretty much straight across at this point, are their concentrations changing? They're not, right? So they all now hit sort of equal concentrations, not equal concentrations, but they've maintained their concentration or constant concentration. And right here, where that occurs is where equilibrium basically has been reached. So graphically, you can see it. You'll initially start to see in this case a pretty steep decrease in your reactants because that's all you got. Going to cause a forward reaction to occur. As products start to rise, you're going to eventually get those reverse reaction happening. Everybody's not going to decrease and increase as much, and eventually everybody's just going to level off basically. And at this point, they're just maintaining, and they will continue to maintain those concentrations again. As long as you don't do anything to screw up the equilibrium, they'll just continue to do that basically, and they'll keep those concentrations continuing. Any questions on that there? Now, as I said before, if we look at this reaction here, come back, there we go. We got our H2O plus our CO plus our H2 and CO2. Initially, all we have are these guys present. So we should start to see really a decrease in these guys because the only option is our forward direction in this case. At this point, we should start to see an increase happening in these guys. And again, just like we saw in that last chart, at some point, we'll start to see a little bit of a decrease in our reactants going away because our products are starting to make more. And again, they will eventually level off until equilibrium is met, and we'll get that reverse reaction occurring. And again, it will eventually hit the rate of that forward direction will equal the rate of the reverse direction. And that is when equilibrium has been met. And again, graphically, that's what we saw in the graph where basically everybody just levels out basically on the graph. So when you're looking at a graph, that's really where you want to kind of figure out where equilibrium is, where you start to see everybody's constant concentrations occur. So why don't we consider this reaction here, and let's say that we did get the system to reach equilibrium, but then we decided we want to add more water to this equilibrium. So we want to dump in some more water or steam, really, in this case, this is a gas. So what I want you to think about is if I were to take this reaction that's at equilibrium already, and I add more H2O to it, what will happen to everybody's concentrations? Will they go up? Will they go down? Will they stay the same? So take a moment and think about how everybody may change, and then we'll talk about what should be going on in this case. Okay, so let's take a look. So first off, this reaction now is, before we do anything to it, is at equilibrium. So what that means again is that the rate of the forward direction will equal the rate of the reverse direction. Now, if we do something to screw up the equilibrium, which is what we're going to do here in a second when we add the water to it, it will eventually, these type of reactions will always find a way to get back to equilibrium. So even if you do something to these reactions, you could do it a bunch of times. You can mess it up and let it get back to equilibrium. You can mess it up again and get them back to equilibrium. It will always find a way to get back to an equilibrium state of the rate of the forward direction, and the reverse direction will equal each other. So one of the nice things about these reactions are you can frankly screw them up a lot, and they will always find their way back basically by themselves to get back to equilibrium. And that can be very advantageous to you if you're doing some type of experiment where you maybe need the reaction to go one way or the other way, and you can kind of force it to do so. So in this particular case, we got everything going nice. We got the rate of forward direction and the reverse direction equal each other. Then we decide to add some water, which is right here. Right? When I add water, what will happen to the concentration of, say, H2 and CO2? Will it go up? Will it go down? Will it not change? What do you think? So let's think about what's going to happen in this case. When I add more water, right? I now will have more or less reactants. More. And what helps a reaction occur? More things or less things? More. So when I add water, right, I am now adding a lot more reactants, which means in comparison of reactants to products, most likely the reactants are going to start reacting, right? Which is going to cause the forward direction or the reverse direction to occur in this case. It's going to cause the forward direction. So by adding more reactants, just the availability of more reactants is going to cause more collisions for the reactant side. And that's going to actually force probably the forward direction here to occur because of that messing up of what you just did there, right? By adding that. And if the forward reaction is going to occur, the concentration of H2 and CO2 should go up, down, or stay the same. It should go up, right? Because I'm going towards the forward direction. I'm going towards the product side, and I should be making products at this point. So we actually should see an increase in the H2 and CO2 concentration, because basically what we just did is kick in the forward direction, basically, right? Going towards the product side. With that being said, that would mean that the concentration of CO in this case should go up, down, or stay the same. What do you think? It's almost a 50-50 shot. It's not a no change in the situation. It's going to be, in order to make products, you need to use up reactants, right? So if the forward direction is going, your reactants are going down, right? Your product should be going up, right? And that's because the reaction is going towards the product side. That's the only way you can make it. We should see the concentration of CO go down because, again, that's the only way you can make products. How about the H2O? What will happen with it? Well, the H2O will actually be kind of maybe a special case. It is first going to go up because you added it, right? So you artificially added a bunch of it that's going to cause it to jump. But once you've added it and that forward reaction starts to occur, we then should see its concentration go back down. Yeah. It may actually end up higher than it started with, only because you artificially added it higher, right? But the trend that you'll eventually see is it'll go up because you added it, but then it should start reacting with CO in this case, and they both should be coming back down in terms of their concentration. The product should be going upwards because, again, we're causing the forward direction to occur. Question on that there. And again, it will again reach equilibrium at some point once you do that. So at that point, when you add the H2O, you messed up the equilibrium. The way it will get back to equilibrium is it will go towards the product side, make some more products, and then it'll come back to the same rate again. Question on that? Yeah. You can if you know really the initial amounts, the initial concentrations of what you started with. And in a sense, if you know kind of the change, you could calculate. If you know the change part of it, you could calculate what you'll end up with at the end. Yeah. Other questions? And we'll do some calculations later on where we start with, for example, reactants and figure out what everybody will end up at equilibrium, reactants and products to start with now. Other questions? All right, so let's take a look at another same reaction, but in this case, we want to add H2 to this equilibrium. So again, we have a system that's at equilibrium, and we're going to add, in this case, we're going to add H2 to it. So when we look at H2 in the reaction, it is on the product side. So when I add H2 in this case, will the forward reaction or the reverse reaction actually take place? Yeah, so in this case, we're actually adding more products. So we're going to have a lot more products and reactants, and that's really going to ultimately cause the reverse reaction basically to take place in this case. Because of that, we would expect the reactant concentration to increase or decrease. Increase, right? We're heading towards the reactant side, so we should be making some more reactants. The only way we can make more reactants, right, is to use up our products in this case of the reverse reaction. So we should expect the CO2's concentration to go down in this case. And much like we saw in the first one there, the H2 will really go up, but ultimately it's going to come back down. And again, it just goes up because you artificially added it. But overall trend really for it will go back down because it's needed along with the H2 and the CO2 are both needed, obviously, to cause that reverse reaction to occur. Any questions on that there? All right. We'll revisit that a little bit later on. That's basically kind of what's known as the Le Chatelier's principle, and we'll talk about that in a little bit more depth later on this chapter. Good zoom. All right. So that we saw. So let's talk about the equilibrium constant. Now, if we have a reversible reaction like this, we can write an expression for it, which is known as the equilibrium constant. This is capital K, which is the equilibrium constant. It is not to be confused with the K that we just talked about in the previous chapter, which I'll dramatically draw as a small k, is the rate constant, right? So they are a little bit different. So capital K is the equilibrium constant, lowercase k is the rate constant. And we could write a equilibrium expression for this reaction, which is essentially the concentration of our products divided by the concentration of our reactants. So it's basically products over reactants. And in this case, you get something like 4.63 times 10 to the minus 3. In general, you take the products over the reactants. We do, in this case, use the coefficients as the exponents when we do so. So the coefficients are the exponents. Here, the coefficient obviously is 1, which is why there is nothing written in this case. So all of our products over our reactants, using the coefficients as the exponents, will give us our equilibrium constant. An equilibrium constant, although a lot of times they beat into your head units, 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 K typically does not have units. Yeah, so no units. It is really just a number that we see. And the equilibrium constant, much like the name implies, is a constant value for a reaction, the way it is written, at a specific temperature. Temperature, as we will talk about, is the only thing that can affect the actual value of the equilibrium constant. But if you do not change the temperature, then the equilibrium constant will always be the same number for that reaction, no matter what happens. Now, what does that number tell us? Let's just say, for example, I had an equilibrium constant that was considered a large value. If I have a K value that is large, when I reach equilibrium, would I mainly expect to have reactants or products present? So the equilibrium constant is calculated right here, products divided by reactants. So if I have a large value, should I have reactants or products there? It is products, right? So mathematically speaking, if you take a large number on top divided by a small number, you get a large number, right? So when you have a large value of K, it means that when you reach equilibrium, you mainly have products, or you mostly will have products present. Same thing if you have a small value of K. You just think about it mathematically, the only way to get a small value is you would need a small value up on top and a larger value on the bottom. And that would mean that I would mainly have reactants present. There's absolutely different degrees of that. You could have really large K values where ultimately the reaction is still a reversible reaction, but is pretty much all going to the product side. You could have extremely small values of K, like to the minus 36, for example. And that would mean that you mainly have just reactants, not much is going to the products. Like I said, a really large value of K, you could have to like the 24 times 10 to the 24, 10 to the 56. They were super really large values as well. So you could have anywhere in between as well. What is considered a large value for K? Anything above the big number of 1. So anything above the big number 1 is considered a large value of the equilibrium constant. Anything less than 1 is obviously considered more of a small value. So in general, if you see like a negative exponent associated with K, then it will probably be considered small. And if you have anything above 1, essentially would be a large value. Now, when we have these, as I mentioned, there are different degrees of large and small, and we'll see them as we go through different chapters. But again, you could have a extremely large one, which essentially is a one-way street, or you could have a really small one, which is also essentially a one-way street. Even if you have a really large value of K or a really small value of K, which would mean you pretty much only have products or you only have reactants, these are still reversible reactions, which means even at the largest values of K, there is still some products coming back the other way. It's just super, super small, but there's always that reversible sort of process occurring, even at sort of the outer ends of the K values and stuff like that. Now, it is always going to be a constant value regardless of what you start with. So what I mean by that is you could do a reaction for this guy here, and you could do like 5 different experiments. And let's just say, for example, in the first experiment, you started with just reactants, no products. Let's say in the second experiment, you started with like products, but no reactants. Let's say in the third experiment, you had a little bit of reactants, a little bit of products, and forth and so forth along the way. No matter what happens, as long as the temperature stays the same in all 5 of those experiments, the equilibrium constant should be the same value, and you'll get the same proportion. And that's sometimes what people have a hard time with. They're like, in the second experiment, I used a lot more reactants than I did in the first. How can I end up with the same equilibrium constant value? And you will, regardless of what you start with. Again, you can start with all reactants, all products, a little bit of everybody, all goes for a swim together, but they will eventually all end up at the same equilibrium constant value. So as long as you don't change the temperature, you'll do that. And people, like I said, sometimes can't visualize how that could happen. So let's just take a very simple example to illustrate that that could happen. So obviously our equilibrium constant is based off the concentration of our products over our reactants. And again, a reminder, as I might have mentioned before, when we see those brackets, that is concentration, right? And molarity is usually what we are talking about there. Moles per liter is essentially what we're talking about. So let's just say that our equilibrium constant at 25 degrees Celsius for all these experiments are going to want to be 2, right? Now, if I wanted to get to 2, right, I could get to 2 a lot of different ways. I could take 4 divided by 2 is equal to 2. I could take 2 divided by 1 is equal to 2. I could take 8 divided by 4 is equal to 2. These are all different numbers, basically, right? And that represents what's going on here, but they all come to the same ratio of 2. So even though you start with like all reactants in one case, or you start with all products, or you start with a little bit of everybody, when the rate of the forward reaction and the rate of the reverse reaction equals each other, and you take that ratio of products to reactants, you'll end up with the same ratio every time. That will give you basically the same equilibrium constant value every time. The only exception is if you do change the temperature, you will get a different value of K. Now, let's just say I did the exact same experiments, not at 25 degrees, but say I did it at 50 degrees. What would happen is I could do my 5 experiments at 50 degrees Celsius, and I will get the same equilibrium constant every single time at 50 degrees. When I compare the equilibrium constant at 50 degrees to what the equilibrium constant is at 25 degrees, those numbers will be different. Yeah, so that's what we're talking about. So if you change the temperature and you compare the K value at one temperature versus another, you will get a different value. And that's the only thing that could affect the value of K. But if you change the temperature to 50 and then do a bunch of experiments at 50 degrees Celsius and you want the K value at 50 degrees for all those experiments, they all should be the same K value, are pretty much identical. If you did all the experiments at 25 degrees and want the K value for all those experiments, they all should be the same value. But when you compare the 2 different temperatures, you'll get 2 different K values for those 2 different temperatures. Question on that there. All right, that's something to ponder.